Hi everyone, welcome to the exercise class. Today I'll be capturing the content of the exercise sheet for this week, which are two things. So the first thing is I'll be talking about the particle in a finite well and how the wave functions of this particle look like and what are the energy eigenvalues of such a particle. And second, I'll talk about a method that was used in a lecture to approximate how the behavior of the wave packet looks like in the limit of the time going to infinity. And for that, in the lecture, there was this method used, which is called stationary phase approximation. So I'll just explain how exactly that method works. Okay, so let us then start with the particle in a finite well. So a particle in a finite well is kind of one of these standard problems that you would have in the quantum mechanics course. And essentially, this problem is nothing special. In a sense, it's just about a particular potential, which has a very simple form. And it's about taking this potential and solving the Schrodinger's equation to find the energy eigenvalues that a particle might have when introduced to this potential. And a finite well is probably the simplest potential one can take and analyze. And for example, in physical modeling, this kind of potential, finite well potential, can be used to describe the potential, for example, of the ions in the crystal structure. And then if you want to somehow describe which are the bound states of the electrons in such a crystal structure, you just have to consider its bound states with respect to this collection of finite wells. Okay, so the finite well is the following potential. So this is, let's say, u of x, this is x, and it's just a well, square well like this, going from minus a to plus a, and its depth is minus u0. And what we'll be trying to do, we'll be trying to solve the Schrodinger equation to find the energy eigenvalues that the particle might have when introduced to such a potential. So mathematically, we can just write that u of x equals minus u0. And we assume that u0 is just a positive value, which denotes the depth of the well. And it's minus u0 if modulus of x is less or equal to a. And the potential is 0 if otherwise, so if modulus x is bigger than a. And for this problem, the states that we are interested in are bound states. So the states for which the energy is less than 0. So E less than 0. So because we know that E is less than 0, then we can already say that we can just denote E as minus modulus E. So why are we only interested in the bound states? Well, because if we assume that the energy of the particle is bigger than 0, then that essentially means that for this particle, this potential well does not really change anything, and the solution of the Schrodinger equation for such a particle would be just a plane wave. And we are not here interested in the plane waves, we're just interested in the bound states which are normalizable. So maybe I'll just note it here that for E bigger than 0, the solutions are plane waves. For a bound state of energy E, we can also note that the energy measured with respect to the bottom of the potential. So for bound states, the energy with respect to the bottom of the potential is, let's call it E tilde, equals E minus U0 equals U0 minus modulus E. Okay, so these were just some notes about the energy and where the bound states are in this case. And now we have to proceed to solve the Schrödinger's equation. So for to solve the Schrödinger's equation, we just need to examine how the equation looks like in different parts of the x-axis, and then essentially for each part, for each region of the x-axis, solve it separately, and then just kind of glue these solutions together using the boundary conditions on the boundaries of these regions. So what we need to write is Schrödinger equation for different regions. And then plus to kind of bring this all separate solutions to one joint solution over the whole x-axis. Then we need boundary conditions. Okay, so the Schrödinger equation, what we're trying to solve here. So another note is that we're trying to find in this like standard problems, we're trying to find stationary states, which means that we're not trying to find the states which would depend on the time. So we're just trying to find the states which are just stationary without any dependence on the time. So essentially, like we can, what we're trying to find here is are the eigenvalues of the Hamiltonian that we have. So we have the Hamiltonian H, and our idea is to find the eigenfunctions psi and also the eigenvalues E that correspond to these eigenfunctions. And the Hamiltonian, as we know, we can just write it as minus h squared over 2m, second derivative of psi. This is just the operator, momentum operator, p squared over 2m, plus u of x psi equals e psi. So E, again, is just the value of, eigenvalue of energy. So hence we arrive to the differential equation. The second derivative of psi over x equals minus 2m over h squared e minus u of x psi. So let us call, just for now, to analyze how the solutions look like to this differential equation. We'll just write that alpha of x as minus 2m over h squared e minus u of x. And this is, and let us analyze what is the sign of alpha in different regions. So for this particular potential, we only have two distinct regions. So the first region is when modulus x is bigger than a. And alpha of x, which is minus 2m over h squared e minus u of x, in this region is bigger than 0. And hence, the solutions to the to this differential equation here, as we know from differential equations course, these are just the real exponentials. So wave functions are real exponentials. Okay. Yeah, maybe if it's not exactly clear why this is bigger than 0, then so for this region, when modulus x is bigger than a, u of x equals 0, right? And hence alpha of x would be minus 2me over h bar squared, and e is less than 0, so alpha of x will be bigger than 0. And the second region is x when modulus x is less or equal to a. And for that case, alpha of x would be negative. And again, looking back at the differential equation, we can already see that the wave functions are just these trigonometric functions, like cosine and sine. Okay, so now we already have kind of an idea of how the function psi looks like. So we know that, so again, maybe let's draw the potential. So we know that, so this is u of x, this is x, this is, let's say, psi of x, this is x. These are minus a and a. So we know that somehow on the outskirts, where x is less than minus a or x is bigger than plus a, like this wave function behaves as an exponential, and we'll later see exactly how it behaves. And in the between, well, there is some kind of trigonometric function. Okay, good. So this is, we already have the intuition. Then another observation that we can make is that we can look at our potential, finite well potential u of x again. We can note that u of x is an even function. So it's an even function of x because, yeah, you can see it that already on the plot that it's symmetric. So u of x equals u of minus x. This is trivial. And this actually gives us a pretty big advantage in terms of finding out the bound states, because it means that the bound states are either symmetric or antisymmetric. I'll give an explanation in a moment. So the bound states are symmetric or anti-symmetric. So why is it so? So because u of x is an even function of x, then essentially the Hamiltonian, if we look at it again, which is just p squared over 2m plus u of x, also acts like an even function. So it acts in a symmetric way, because p squared would just give you the second derivative, which so we don't care about the sign effects. and which means that the Hamiltonian commutes with the parity operator P that we looked at before. And the one thing we know about the parity operator is that the eigenfunctions of the parity operator are either odd or even, so they are either symmetric or antisymmetric. And another thing that we know is that if two operators commute, then they actually share an eigenbasis. So essentially they have the same set of eigenfunctions. This is quite trivial to show. I think it would be a nice exercise if you do it. But this is just something that is true for two operators which commute. And from this, we can actually make a conclusion that if this Hamiltonian and the parity operator share the set of eigenfunctions, then that essentially means that the eigenfunctions of this Hamiltonian are either symmetric or antisymmetric, and hence we can divide our search for the eigenfunctions of this Hamiltonian, which we'll be doing now, into the search of the even solutions and the odd solutions. And this is a good trick to use if you ever see a potential that is symmetric, or the potential that you can make symmetric, then then immediately you need to know that okay, then I only need to then I have kind of reduced the number of degrees of freedom that I, for example, need to put in into these coefficients when I solve the differential equation. Now I can just solve the differential equation to find the even solutions, and then I can solve the differential equation to find odd solutions. Okay, so since we made this conclusion, let us first look for even solutions. Okay, and again, we're just looking at the two regions. So modulus x less than a and modulus x bigger than a. So first we look at modulus x less than a. Then we have the following differential equation: second derivative of psi equals minus 2m over h bar squared e minus u0 psi. This is just minus 2m over h bar squared u0 minus modulus e psi. So u0 minus modulus e is bigger than 0, again because we're looking for the bound states. Then let us denote the kind of the coefficient that comes up in this differential equation as k squared. So it's 2m over h bar squared v0 minus modulus e. This is bigger than 0, and we just choose k bigger than 0. Please keep in mind that k is not just some value. Its k still depends on the energy E that we're trying to find. Okay, but then, so then we get to the to our simplified differential equation, which is the second derivative of psi equals minus k squared psi. And we're looking for an even solution, so the function has to be even. So obviously the solution to this equation would be psi of x equals cosine kx, or modulus x less than a. So to to be completely precise, one can, of course, include some some coefficient here, just some constant here. But here I will not do it because this constant we can also include this constant from considering the solution in the region where x is bigger than a. And here it's a bit unnecessary. Okay, so now let us look at the second region where x is modulus x of is bigger than a, right? And here we have essentially the differential equation where u of x equals 0. So we just have minus 2m over h bar squared e minus 0. Sorry. So here we just have 2m modulus e over h squared. Sorry. Then let us denote as kappa squared 2m modulus e over h bar squared. So kappa we choose bigger than 0. Again, bear in mind that while kappa squared is a constant for the particular value of the energy, it is still dependent on the energy eigenvalue E that that we're trying to find. Okay, and since we introduced this notation, the differential equation just transforms into the second derivative of psi equals kappa squared psi. As I already mentioned, the solution to this differential equations are just exponentials. However, we have a particular kind of condition on the exponentials that we can use, which is that we need exponentials which decay as we go to infinity. So this can be seen as a condition for a bound state, which is kind of easily justifiable if you think that the bound state has to be normalizable, and it also has to be somehow bound to the potential that you're considering it in. So essentially that means that the bound state has to be significant only in the neighborhood of the potential that you're considering. So it's kind of the particle is bound with the potential. And given this condition, we can easily see that psi of x is then some constant. That's exactly the constant I was talking about before. E to the power minus kappa modulus x for x bigger than a. And here we see indeed that for x going to infinity and minus infinity, because kappa is chosen bigger than 0, psi of x, so the limit of psi of x modulus x goes to infinity equals 0. So infinity, I mean plus minus infinity. Okay. So then we can summarize our findings for now. So we found that psi of x equals cosine kx if x modulus is less or equal than a, and a e to the power minus kappa modulus x if x is bigger than a. Okay, just a small interlude about k and kappa. So we can see that k and kappa, so k squared and kappa squared satisfy a simple relation, which is k squared plus kappa squared. So coming back to the definition of k squared, is just 2m over h bar squared, u0 minus modulus e. It's minus, no. And kappa squared is just 2m modulus e over h bar squared. So what we get is 2m u0 over h bar squared. Okay, so we have this relation. Then what we also do is we can introduce unit-free constants. So because so this is of course just introducing some additional proxies, but this will come in useful when we will look at how we can graphically find and characterize the solutions. And this is easier to do if the units in which you're trying to solve the equations are unit-free. So let us introduce unit-free constants. So eta will be equal to Ka bigger than 0 because we chose K bigger than 0. Then psi, my favorite Greek letter, saying it ironically, I hate to draw it. It's equal to kappa A, which is also bigger than 0 because we chose kappa bigger than 0. And the last one is Z0 squared, which is equal to 2m u0 a squared over h bar squared. So if you're curious about this choice, well, this will become clear later. One thing to note about this unit-free constants is that the first two constants, eta and psi, they are essentially, as I said, they're proxies of k and kappa. They're just unitless. And as k and kappa depend on the energy E that our particle has, eta and psi also depends on E, the energy. However, the last constant, Z0 squared, it does not depend on energy. It just depends on the initial setup of the problem. So the mass of the particle, the width of the well, and also the depth of the well. So essentially, the bigger, so the larger, or so maybe not larger is not a good word. So the deeper or the wider the well is, the bigger Z0 becomes. And also for the shallow, so for shallow or narrow wells, Z0 is smaller. Okay. Now, following from the connection between k squared and kappa squared, we can formulate the similar connection for their proxies, which are eta squared and psi squared. So we can see that eta squared plus psi squared are, which would be equal to k squared plus kappa squared a squared. And k squared plus kappa squared we already derived here, which is 2m U0 over h bar squared. Sorry. 2m squared, a squared. This is equal to z0 squared. Okay, perfect. Fine. Now, so let us keep this in mind that eta squared plus psi squared equals z0 squared. And now let us complete the construction with the last ingredient that I already mentioned in the beginning, the boundary conditions. So for the wave function, we have two boundary conditions. For psi, for the continuity of psi and its derivative, psi prime, at modulus x equals a. Okay, so from the fact that psi is continuous at x equals a, we get that cosine ka equals a e to the power minus kappa a, and from the fact that psi prime, so the first derivative of psi is continuous at x equals a, what we get is minus k sine ka equals minus kappa a e to the power minus kappa a. Okay, and here we actually already can see that the to determine the connection between, like for example, in this case, kappa and k, one additional one, we don't even need the constant a, because it will just go away. We can, because we can just divide the first equation by the second equation. A note, so you might be wondering why I only use the boundary condition at x equals a. Well, I keep in mind that the function that we just found is even. So it's an even solution. So the boundary conditions for x equals minus a will just mirror this boundary conditions that we have at x equals a, because the function is even. So here, from these two equations, we divide one by another, and we find a relation between kappa and k. So we already had a relation which is there on the top of the page. So that would be the first relation, and now the boundary conditions allow us to find the second one, which is k tangents of ka equals kappa. And to translate it in our unitless constants, our unitless variables that we just introduced, we can write this as ka tangents of ka equals kappa a, which means that in terms of psi and eta, it's psi equals eta tangents eta. Okay, and what does this mean? This means that we have two equations which govern psi and eta, and from that we already are able to find out psi and eta, and hence the corresponding eigenvalues of energy E, which are encoded in the psi and eta. Okay, so for even solutions, we get the following relation. So the first is eta squared plus psi squared equals z0 squared. And the second one is psi equals eta tangents eta. And psi and eta bigger than 0. One can solve this numerically. And bear in mind that z0, the value of z0, is just given by the problem itself, because it is determined by the mass of the particle and by the size and depth of the well. However, we are able to see like potentially how this solutions look like if we just consider the first upper plane of the if we plot psi and eta against each other, and then we can just plot both of these functions and see where they intersect. So we just plot the solutions to the first. What I mean is that we plot the solution to the first equation, then we plot a solution to the second equation, and then the intersections would be the solutions to both of them. Okay, so let me do some preparation here for the eta tangents eta. So we have here 0 pi over 2 pi 2 pi. Yeah, let me use different colors. So the first equation, which is eta squared plus psi squared equals z0 squared, it just describes like 1/4 of the, for eta bigger than 0 and psi bigger than 0, it just describes 1/4 of a circle with a radius z0. So suppose goes like this: z0, z0. So this is eta squared plus psi squared equals z0 squared. Okay, the next one, we plot the function psi equals eta tangents eta. And this function looks like following: here, here, and so on. It's periodic. Okay, and this allows us to, so this is psi equals eta tangents eta. And this allows us to see what are the solutions quite easy, because what we arrive to is that we have one intersection here, second intersection here, and that's it. Of course, the number of these intersections depends on the value of z0, like how big the circle is, and how many of these branches of tangents it will intersect. But we can already make some conclusions just from this picture. So this picture describes a situation where we have exactly two even bound states. And the first intersection here, so the first intersection happens around eta pi over 2. And of course, like if z is really small, I don't know, it goes here, of course this wouldn't be exactly near pi over 2. But for large z0s, so the bigger the potential is, this intersection would happen around around eta equals pi over 2. And again, imagine that this circle grows bigger and bigger. Then essentially the number of intersections, which denote the number of the bound states, even bound states, it will grow. So bigger z0, more bound states, which totally makes sense because the wider or the the deeper the potential is, there are more possible energies that it can bound. But one thing to note is that no matter the value of Z0, no matter how small, sorry, no matter how small the potential is, we will always have the first bound state. Because the circle will always intersect, no matter how small it is, it will always intersect this first branch of the tan function. Yeah, and this is an important conclusion to keep in mind, that we will always have a bound state, no matter how small the well is. Okay, so this was the analysis with regards to the even solutions. We can carry out the similar analysis if we consider the odd solutions. It will be just slightly different. So similarly to the even solutions analysis, what we need is for the solution in the well itself, it has to be a trigonometric function, and it also has to be odd. So hence the easy conclusion here is that it has to be a sine for x less than a, and for the x modulus x bigger than a, yeah, what we have to do is also have a function which would essentially die exponentially. So then we would have like our same function minus kappa x for x bigger than a. Then essentially matching at x equals a for psi and psi prime gives us a bit of a different connection between psi and eta, which is psi equals minus eta cotangents of eta. And hence, the relevant solutions are the following. So for the odd solutions, we have a corresponding system of equations governing eta and psi. So the first one we keep, eta squared plus psi squared equals z0 squared. And the second one is given to us by the new boundary conditions. So it's psi equals minus eta cotangents of eta. Psi eta bigger than 0. Okay, then we do here the same thing. We draw psi against eta. Again, some preparation here. Pi over 2, pi, 3 pi over 2, 2 pi. And again, we have two functions. So the first function we already know, it's just a circle. This z0, z0. And the second function is minus eta tangents of eta, and it will look like this: 1, 2, and so on. So here we have two bound states, two odd bound states. An important thing to notice here is that actually there might be situations for small z0s, like for example, if z0 is less than pi over 2, like, and then the circle goes here, that there might be no odd solutions, not bound, no bound odd solutions. So for z0 less than pi over 2, no bound odd solutions. However, we still remember that if we take into account also even solutions, there is always at least one even solution. So maybe it's good to portray everything on the same picture. So let me just copy this one. And also draw here the even solutions that we found, which here, here. And so we have this one even, this one odd, this one even, this one odd, and so on. So two things. First, we always have an even bound state. Second, if we have more, then from this picture, we easily see that even and odd solutions, yeah, so there's first even solution, then there is odd solution, then there is even solution, then there is odd solution, so they interchange. Yeah, okay, so now finally, what about the eigenstates for the wave function? Well, we can sketch them. We already know kind of how they look. So sketching, energy, eigenstates. So suppose that we took three energies, E1, E2, and E3, which corresponds to the ground state. So the ground state is this first even state here. Then the second state, which is odd, and the third state, which is even again. So E1, E2, E3. So first, let us draw our finite well. So finite well here, which is not that symmetric. Sorry about that. Minus A, and then we have the three energies, which are, suppose, E1, E2, and E3. And now let us draw how the wave function looks like. So for the first state, which is a ground state, which is even, so let us draw the bounds here. So here we have an exponential, then we have a cosine, then we have again the decaying exponential. So this is the ground state, which is even. Then for the second state, it's odd. So on the outskirts, we again have the decaying exponential. In the well here, we have like a cosine, and then we have we have a sine, and then we have a decaying exponential again. So this is the first excited state, which is odd. And then finally for the third one, but I think you already understand how this works. So we have a decaying exponential, then we have a cosine with a higher frequency, then we have a decaying exponential again. So it's second excited state, which is even, and so on. So I think this is all for this problem. Yeah, the takeaway message here is that the problem is nothing special. Like essentially, mathematically, is just solving the differential equation. Two things to remember is that here, because the potential is symmetric, we can look for the even and odd solution separately. We have this privilege. And second is that the wave functions, they you should kind of have an understanding of how the wave function looks like, and like intuition of how it looks like, because for the bound state, one thing we have to remember is that the wave function has to decay on the in the infinity, in the limit of infinity. So which essentially means that it just dies out, and it's an exponential. And it's a decaying exponential when x goes to infinity. And within the region where it's confined to this to this well, to this potential, it's harmonic, like its eigenfunctions are harmonic, so it's either a sine or cosine. Yeah, and it behaves in that way. Okay. And of course, what you can also do at home is that you can just like open MATLAB or something and plot like how the solutions look like I just plotted here in the schematic way for different values of z0. And what are the exact solutions for xi eta. Okay, now coming to the second part, which is the part where we look at the stationary phase approximation. Okay. So one quick note that I have to say is that this exercise is extra. You don't have to do it. I'll look at it now, almost completely. You also don't need to know this for the exam. Like this is not a material, or this is not a mathematical method that would be needed in the exam. So this exercise and my explanation just serves the idea of making this black magic of approximation that happened in the lecture less of black magic and more of just, oh, it's just maths, and or just a method of mathematical physics that one can use to calculate a particular type of integrals. So let us start with making this magic less of a magic. Yeah, so we used it in a lecture to approximate the behavior of the wave packets in the limit of the time going to infinity. Another example where this method is used, I think I can vaguely remember that we used it for something, in my courses we used it for something as approximating some types of Brownian motion of the particle, but generally sometimes these integrals come up quite often in mathematical physics. So we're looking at the integral I of t, which can be written as an integral from minus infinity to plus infinity, e to the power it f of k, g of k, dk. And the idea here is that these integrals are generally quite hard to calculate exactly, especially when the functions f of k and g of k are not that nice. And the idea here is that the exponential, the first exponential that we have, e to the power it f of k, of course it can be written out as just a combination of sines and cosines. And if the function f is kind of fast enough, so if these oscillations happen fast enough, then one can show that this integral, the biggest contribution to this integral is made in the neighborhood of so-called non-degenerate critical points of f of k. So the kind of the calculation, the idea of the calculation is that one needs to find this non-degenerate critical points of the function f, which means it's such points k such that f prime of k equals 0. So the first derivative equals 0, but the second derivative doesn't. And now I will show why, where does this argument come from, that the most contribution that comes to this integral comes exactly from the neighborhood of this critical points, non-degenerate critical points. So for this, let us consider, so maybe I just noted here that the largest contribution to the integral contributions maybe to the integral come from such points k. So from their neighborhoods. Okay, so for this, let us consider the integrand in the delta neighborhood of such an arbitrary. Okay, so let us consider the integrand in the delta neighborhood of just an arbitrary point k, or k0, let's call it. So let us consider the integrand in the neighborhood of an arbitrary k0, and look at the integral of what is the integral in this neighborhood. So what I'm proposing to do is to look at the integral from k0 minus delta, so it's a delta neighborhood, to k0 plus delta, and then we write the integrand, e to the power it f of k, g of k, dk. So because we can choose the neighborhood arbitrarily small, what we can assume is that, so the g of k, the function g of k, we can just assume that in this neighborhood, it is approximately g of k0. So we assume that it is g of k0, and we're left with this thing. So for this, we assume that j of k is approximately j of k0. Then we need to do the next approximation, which is let us expand f of k in the neighborhood of k0 in terms of its Taylor series. So, and we will do it to the first order only. So f of k equals f of k0 plus f derivative of f at k0, k minus k0. Okay, great. Then let us insert this into the integral. IT. So let me, just for convention, call the f of k0 f0 and f prime of k0 as f of prime 0, just to make it easier. So we have f0 plus f0 prime k minus k0 dk. Okay, this is something that we can integrate, right? So what we have here would be g of k0 e to the power it f0 minus it k0 prime 0. And here we're left with it 0 prime k dk, integrating from k0 minus delta to k0 plus delta. Okay, and then we're left with, so this exponential we can definitely integrate. We're left with g of k0 e to the power itf plus it f0 it f0 prime minus e to the power itf minus it over itf prime 0, which equals to g of k0 e to the power itf0 to, so this would be 2 sine of t delta f prime 0 over t f prime 0. Let us look at this expression more carefully. So what we see here is, since we can choose, since we're looking at the equation in the limit of t going to infinity, and also we can choose the neighborhood as small as we want. Kind of the thing in the nominator, it can be like anything between 0 and 1. It can be anything between 0 and 1. Moreover, we can kind of always choose t, like the time big enough so it would be it would be 1, for example. Like these two are like constants, and in the last thing but not the least, we have in a denominator we're dividing by the f0 prime, and since all the other values, yeah, they can be, so the sign just oscillates. The other two are just some constants which depend on g at k0 and f at k0, but we divide over f prime, so we divide by the first derivative of f at the point k0. And the bigger, so the smaller that derivative is, kind of the bigger the whole value gets, essentially, of this equation, of this expression, and which kind of gives us the intuition that okay, if the derivative of f in the point k0 is equal to 0, then then the contribution of the neighborhood of this point k0 would be the greatest, because this kind of short calculation of approximating how the contribution would look like in the first order approximation of f at this point showed us that in this approximation the contribution would actually be infinite. Okay, so from this, then we can argue that the contribution is largest for points k0 such that the first derivative of f at k0 equals 0. Okay, and now let us consider an example, which would be a function f, which has only one non-degenerate critical point, so only one such point, k0. So with only one non-degenerate critical point. K0. And let us calculate the integral I of t for such a function f of k. So we just concluded that to calculate this integral, we only need to calculate it in the neighborhood of this point k0. Fine. And what we also need to do is we need to write out up to the second order the Taylor series of the function f in the neighborhood of the point k0. So then what we can write is f of k equals f of k0 plus f prime of k0, k minus k0, plus second derivative at k0 over 2, k minus k0 squared. So because the first derivative equals to 0, then the second term in the expression goes away. And we're only left with these two. Again, for convenience, I will just label f of k0 as f0, and the second derivative of f at k0 as f0 double prime. And now let us come back to the integral I of t. So we can just approximate it as just an integral in the neighborhood of k0. E to the power it f0 plus f0 double prime over 2 k minus k0 squared g of k0 dk. Okay, now we take out everything that we are not integrating over. So we get is e to the power it f0 g of k0 integral of k0 minus delta k0 plus delta e to the power it f0 double prime over 2 k minus k0 squared dk. Okay, here we use kind of another trick. So another trick is look at this integral, which is at this point taken from k0 minus delta to k0 plus delta. But if we look at this integral, it is kind of a Gaussian. I mean, not kind of, it is a Gaussian. And then we know that actually the most contribution this Gaussian gives us is around the point k0, which means that actually we can just extend the limits of integration from k0 minus delta to k0 plus delta to integrating from minus infinity to plus infinity, because kind of the contribution of the tails of this Gaussian is neglectable where compared to the contribution that its main part gives us. Okay, then, and that makes it like extremely easy to integrate if we have it from minus infinity to plus infinity. So we have dk. And what we get is the following. E to the power it f0 g of k0 by square root of 2 pi over t f0 double prime I, and this is e to the power it f0 minus ip over 4, which comes from like the square root of 1 over I, g of k0 square root of 2 pi over t 0 second derivative. Okay, so we have successfully approximated I of t by the following. So I of t is approximately e to the power it f of k0 minus I pi over 4 g of k0 square root of 2 pi over t f second derivative at k0. So this is like more or less the explanation of this approximation. Of course, it was a bit hand-wavy, like in a physical way, as physicists do it with the mathematical approximations. But just because from physics we know that kind of a particular function has to it has to be integratable, or so something has to be non-divergent because we have that like kind of physical intuition, then we are able to do some of these hand-wavy things. Of course, if you start to consider the situation like in mathematical sense more rigorously, then you will need probably like, I don't know, 2 more pages of exact proof of like involving like delta neighborhood, epsilon neighborhood, this limit and that limit, which would prove why this works. But like since we're physicists, we're just have the intuition that it should work, and then we arrive to this kind of approximation. Okay, and finally, let us consider this with respect to the case that was in the lecture. So let us consider this for the wave packet psi of vt x, which was written as 1 over square root 2 pi h bar, integral from minus infinity to plus infinity, e to the power it over h bar, vp minus p squared over 2 mu, phi bar p minus p0 dp. So here we're integrating over p instead of k, but that's just the change of the variable. So first, as we learned from our analysis before, we need to find the critical points of the function f. And so critical points of the function f, and the function f is now f of p. In this case, it's vp minus p squared over 2 mu over h bar. So we need to find points where f prime of p equals 0. So if prime of p equals 0, then v minus p over mu equals 0. Then it's p equals v mu. So we found a critical point. It's also non-degenerate because the second derivative of at the point p equals v mu is, so if we take the second derivative, we get here minus 1 over mu, I think. Mu h bar, sorry. Yeah. And it's non-zero. So we have exactly the case that we just discussed when we're looking at the function at this integral where the function f has only one critical point. So we have one critical point, let's label it p0, which equals v mu. Then we can use our formula and approximate psi, or rather the integral in the psi. So it would be 1 over square root of 2 pi h, because it's just a coefficient that was hanging there from before. Then we have the exponential of it f of k0 or f of p0 minus I pi over 4. So what we have here is I, so e to the power it over h. Then we just write the value of function f at the point p0. So I'll just substitute the p with the p0, which is mu v. And then we're still hanging with this I pi over 4. And the last part is square root of 2 pi over t, second derivative of f in the point p0. So 2 pi over t. And we already calculated the second derivative. It's minus 1 over mu h. Okay. So 2 pi goes away. Use a different color. 2 pi, h goes away. Here we're left with mu v squared over 2. Then what we arrive to is mu over t square root e to the power it h mu squared v squared over 2 plus I pi over 4. Minus turn into the plus because here we were taking the square root of, is it correct? It would be I square root of minus I, then, yes. So because we were taking out the square root of minus 1 here, which would turn into plus I pi over 2, and e to the power plus I pi over 2, and then here we would have minus I pi over 4 plus I pi over 2, which would lead to plus I pi over 4. Okay, but most importantly, what we got here is this behavior at t going to infinity. So the wave packet at t going to infinity, the wave function would behave as proportional to 1 over square root of t. Yeah, the shape of it, and yeah, that's how this approximation is done, without just simple saying, oh, it's black magic. We can just see that it equals this. Okay, I think this is everything I wanted to talk about today. There is a question. It should be mu without the power to. Yes, exactly. Sorry, you're right. It's just mu. Thank you. Yeah, so this is everything I wanted to talk about today. Yeah, if there are any questions, please come forward. If not, you can always email me, or just email both of us, and also write us if you want to meet kind of in Zoom person on Tuesday in the office hours. Yeah, otherwise, if there are no questions, I wish you a good end of the week, and thank you for attending.